Hello students, let us solve one more problem on finding Fourier series. If f of x equals to pi minus x upon 2 whole square in 0 less than x less than 2 pi, show that f of x equals to pi square by 12 plus summation 1 to infinity cos x by n square. That means they are already given the Fourier series. We need to find this Fourier series for the function pi minus x upon 2 whole square. Now this function f of x is defined in the interval 0, 2 pi. The function f of x is defined in the interval 0, 2 pi. The Fourier series for the period 2 pi is given by f of x equals to a0 by 2 plus summation n equals to 1 to infinity a n cos nx plus summation n equals to 1 to infinity b n sin nx. Let us take it as equation 1. Now we need to check the even and odd nature of the given function. Okay, since the interval is 0, 2 pi, to check the even or odd nature of the given function, we need to substitute x equals to 2 pi minus x. Means we are checking even and odd nature of the given function in the interval 0, 2 pi for 2 pi minus x. If the interval is minus pi, pi, then we are checking even and odd nature of a given function for x equals to minus x. Okay. Consider f of x equals to pi minus x upon 2 whole square. We shall check for even and odd nature. F of 2 pi minus x equals to pi minus of 2 pi minus x upon 2 whole square. Pi minus 2 pi plus x minus 2 pi minus into minus plus x upon 2 whole square, or minus pi plus x upon 2 whole square, or x minus pi upon 2 whole square. X minus pi we just written as pi minus x upon 2 whole square. Under square is there, therefore x minus pi I have written it as pi minus x upon 2 whole square. That is f of 2 pi minus x equals to pi minus x upon 2 whole square. That is nothing but the given function f of x. Therefore f of x is even in the interval 0, 2 pi, and hence the coefficient Fourier coefficient bn becomes 0. Now we need to find a0 and an coefficient. a0 is equals to 2 by pi integration 0 to pi f of x dx. An is equals to 2 by pi integration 0 to pi f of x into cos n. We shall find these a0 and an by substituting the function f of x equals to pi minus x upon 2 whole square. Okay. a0 is equals to 2 by pi integration 0 to pi minus x upon 2 whole square dx. 2 by pi integration 0 to pi minus x whole square upon 2 whole square is there, that becomes 2 square is 4 into dx. 2 ones are 2 twos are, therefore it is 1 upon 2 pi integration 0 to pi expanding pi minus x whole square using a minus b whole square, that is pi square minus 2 pi x plus x square dx. Next, integrating these terms with respect to x. 1 upon 2 pi into bracket pi square is a constant, pi square into 1 dx is pi square x minus 2 pi into x integration is x square by 2 plus integration of x square is x cube by 3. Here 2 cancels. Next, substituting the upper limit pi, lower limit 0. Pi square into pi minus 2 cancelled, pi into pi square plus pi cube by 3. Next, lower limit becomes 0 because 0, 0, 0. Therefore, it total is 0. Pi square into pi cube. Pi into pi square, pi cube. Plus pi cube minus pi cube becomes 0. Next, we have plus pi cube by 3. That is 1 upon 2 pi into bracket pi cube by 3. Here pi 1 by cancels. 2 into 3, 6. Therefore, we have a0 is equals to pi square by 6. An is equals to 2 by pi integration 0 to pi f of x into cos nx dx. Substituting f of x equals to pi minus x upon 2 whole square, that is 2 by pi into integration of 0 to pi minus x upon 2 whole square cos nx dx, or 2 by pi integration 0 to pi minus x whole square upon 4 cos nx dx. 2 ones are 2 twos are, 1 upon 2 pi. We left with pi minus x whole square into cos nx. Product term, applying the Bernoulli's rule for integration. that is pi minus 1 upon 2 pi into bracket pi minus x whole square into integration of cos nx is sin nx by n minus 2 into derivative of this term 2 into pi minus x into again in derivative of pi minus x is minus 1. Integration of sin nx is minus cos nx by n. Already 1 n is there, therefore this becomes n square. Plus next derivative of this term is 2 into 1 upon n square as it is. Integration of cos nx is sin nx by n square into n is n cube. Between the limits 0 to pi. Since n sin n pi sin 0 are 0, the third term and first terms becomes 0, or the first term and third term vanish. We are left with the second term, that is minus into minus plus 2 into bracket pi minus x into minus cos nx by n square 0 to pi. 1 upon 2 pi into this 2 pi n square minus 2 pi n square taking outside, 1 by 2 pi into minus 2 pi n square into bracket, substituting the upper and lower limit pi and 0. Pi minus pi, cos of n pi up minus pi minus 0, cos n into 0. Pi minus pi in 0, this term is 0. Next cos n into 0 is cos 0, that is 1. We have pi into 1, that is next minus pi. 1 upon 2 pi means here 2 cancels. We have minus 1 upon pi n square into bracket. The value of this bracket is minus pi. Again here pi cancels. Minus into minus plus. n is equals to 1 by n square. A naught is equals to pi square by 6. n is equals to 1 by n square. Thus the required Fourier series is f of x equals to pi square by 6, that is a naught by 2, pi square by 6 upon 2 plus summation n equals to 1 to infinity 1 by n square into cos nx plus 0, there because bn is 0. Or pi minus x upon 2 whole square is equals to pi square by 12 plus summation 1 to infinity cos nx by n square. This term they ask us to show that, therefore we have obtained the required answer. Let's solve one more example. Obtain the Fourier series expansion of the function f of x in 0 less than x less than pi, x minus 2 pi in pi less than x less than 2 pi. Means here they have given two functions in the interval 0 to 2 pi. First function interval is 0 comma pi, second function's interval is pi to 2 pi. Hence deduce that pi by 4 is equals to 1 minus 1 by 3 plus 1 by 5 minus so on. Okay, first we need to find the Fourier series for the given function. Next we need to reduce the obtained Fourier series to this form. The Fourier series of period 2 pi is given by f of x equals to a naught by 2 plus summation n equals to 1 to infinity a n cos nx plus summation n equals to 1 to infinity bn sin nx. In the given f of x, here two functions are given. Let's write those two functions as phi of x equals to x, psi of x equals to x minus 2 pi. Whenever two functions given like this in the interval 0 to 2 pi, let us write like this: pi of x equals to x and psi of x equals to x minus 2 pi. Okay, here you can see even and odd nature of f of x in 0 comma 2 pi. Okay, how to check even and odd nature for this one? We need to write the given function as pi of x and psi of x. Next we need to check even and odd nature. If pi of 2 pi minus x equals to psi of x, then we can say it is a given f of x is a even function. If f of x is odd, if pi of 2 pi minus x equals to minus psi of x, means pi of x equals to plus phi of x, psi of x, then it is even. Phi of x equals to minus psi of x, then it is odd. But here x we need to take it as 2 pi minus x, when we have the interval 0, 2 pi. Okay, we have written pi of x equals to x and psi of x equals to x minus 2 pi. Next we need to check the even and odd nature. Phi of 2 pi minus x, that is equals to 2 pi minus x. Pi of x is what? X. Here we need to substitute x equals to 2 pi minus x. That is phi of 2 pi minus x equals to 2 pi minus x. Taking minus common from these terms, that is minus into minus x becomes plus 2 pi becomes minus 2 pi. That is minus into bracket x minus 2 pi. X minus 2 pi is nothing but our psi of x, right? X minus 2 pi is nothing but our psi of x. That is nothing but minus psi of x. Phi of 2 pi minus x equals to minus psi of x. Therefore, the f of x is odd. You can see here. F of x is odd if phi of 2 pi minus x equals to minus psi of x. Right? When the two functions are given, we need to consider those two functions as phi of x and psi of x, and we need to find the even and odd nature like this. Now we have obtained the given function is odd nature, hence a0 and an coefficients becomes 0. We need to find bn. Bn is equals to 2 by pi integration 0 to pi f of x into sin nx dx. 2 by pi integration 0 to pi x into sin nx dx. Okay, here I have taken f of x as x because the limits are 0 to pi. In the interval 0 to pi, the function is x. Therefore, I have taken x into sin nx with respect to x. Next, applying Bernoulli's rule for this one. 2 pi pi into bracket x into integration of sin nx is minus cos nx by n, minus 1 into this minus 1 by n as it is. Integration of cos nx is sin nx and n already n, sin nx by n, n into n square, 0 to pi. Since sin n pi and sin 0 are 0, second term vanish, we have only first term. That is, taking this minus common means outside the bracket, or minus 1 by n outside the bracket, you can take minus 2 by pi into bracket x into cos nx by n between the limits 0 to pi. Again taking 1 by n outside the bracket, minus 2 by pi n into bracket pi into cos n pi minus 0. Or cos n pi is minus 1 raised to n, minus 2 upon pi n into bracket pi into minus 1 raised to n. Pi cancels. We have bn is equals to minus 2 upon n into minus 1 raised to n. But minus 2 I have written it as minus 1 into 2. Minus 1 into 2 upon n minus 1 raised to n. Minus 1 means it is minus 1 raised to 1. Minus 1 raised to 1 minus 1 raised to n, that becomes minus 1 raised to n plus 1. Therefore, bn is equals to 2 into minus 1 raised to n plus 1 upon n. This is bn. Substituting the values in equation 1 becomes f of x equals 0 plus 0. Since it is an odd function, a0 n coefficients becomes 0. Therefore, first and third term of the equation becomes 0 plus summation n equals to 1 to infinity 2 into minus 1 raised to n plus 1 upon n sin nx. bn is 2 into minus 1 raised to n plus 1 upon n into sin nx. That is f of x equals to summation n equals to 1 to infinity 2 into minus 1 raised to n plus 1 upon n sin nx. This is the Fourier series. Now we need to deduce this to required series. To deduce the series, let us put x equals to pi by 2, then f of x equals to pi by 2. Since f of x equals to x in 0, pi, hence the Fourier series becomes pi by 2 is equals to summation 1 to infinity 2 into minus 1 raised to n plus 1 upon n sin n into pi by 2. Expanding by putting n equals to 1, 2, 3. Here pi by 2 is equals to 2 into bracket, this 2 into bracket minus 1 raised to 1 plus 1 upon 1 sin pi by 2 plus minus 1 raised to 2 plus 1 upon 2 sin 2 pi by 2 plus minus 1 raised to 3 plus 1 upon 3 sin 3 pi by 2 plus minus 1 raised to 4 plus 1 upon 4 sin 4 pi by 2 plus minus 1 raised to 5 plus 1 upon 5 sin 5 pi upon 2 plus so on. And we know that sin pi is equals to 0, sin 2 pi is equals to 0, sin 3 pi by 2 is equals to minus 1, sin 5 pi by 2 is equals to 1, and so on. Using these results, here we get, and transferring this 2 to LHS, pi upon 2 into 2, that is equals to sin pi by 2 is 1. 1 minus sin pi, here we are getting 2 cancels, we are getting sin pi, that is 0 plus 1 by 3 into sin 3 by 2 is minus 1 plus 0 plus 1 by 5 into 1 minus so on. That is equals to pi by 4 is, that is pi by 4 is equals to 1 minus 1 by 3 plus 1 by 5 minus so on. This is a required series.